recording is in progress. You should all see a red dot on your screen.
Yep.
Okay. Very good. We are your audience.
Okay. Can you see my screen all right?
I can, thank you.
Jason?
Affirmative.
Yes.
All right. Okay. So thank you all for being here. My name is Derek Larson. I'm here to present my findings at the Washington Department of Fish and Wildlife, Region 1 headquarters in Spokane Valley, Washington. So let's begin with just an overview of the project. So the Capstone project is based on an investment-grade audit performed by McKinstry, which is the company I work for. My role here is an energy engineer. My primary responsibilities are performing energy savings calculations, but for this particular project, since it hit at the time that we needed to find a capstone project, I was able to talk my superior into allowing me to take more of a lead effort on this. So the intent of this project was for the customer to pursue a design-build project using the energy services company model, which the main component there is guaranteed cost and guaranteed savings, and I'll give a little more detail later on. We're looking at two facilities. There's the main office. It's 2 stories, about 15,000 square feet, and there's also a standalone lab facility that's a little over 5,000 square feet. And these buildings were constructed in the early to mid 2000s. The office was built first, and then the lab was followed a year or 2 later. And this is located in Spokane Valley, Washington, which is right on the Washington-Idaho border. So looking at the building systems, at the main office, it's primarily served by 2 single-duct VAV rooftop units with DX cooling and gas preheat. Each unit has 2 stages of heating and 2 stages of cooling, which is admittedly not great for temperature control. Downstream of those units are a number of series and parallel fan-powered VAV boxes with electric reheat, and those boxes have single-stage electric heat, which again is not ideal because it's either full on or full off. They have electric domestic hot water heaters, so you can see the primary heating source here is electric as opposed to natural gas. They have an automated Logic brand building automation system for full DDC control of all of these systems. The walls are constructed with 2x6 metal studs, R19 bat insulation, R15 rigid roof insulation. That's about what you'd expect for a building of this type, and then double pane 1-inch windows. Here's a picture of one of the rooftop units, as well as one of the VAV, fan-powered VAV boxes. This type of system is fairly common for this type of an office building. And then moving over to the lab, this is served by a single constant volume rooftop unit that's 100% outside air. Whether or not that's necessary is really a question because they don't really use this very extensively as a lab building, so that 100% outside air is likely excessive. That RTU also has DX cooling and gas preheat, again 2 stages each. It does have a variable frequency drive on the supply fan, but it's not actually used to vary the speed at all, so it is a constant volume system. And that's serving 6 electric reheat coils that have modulating SCR control, so they do have very good control over the supply air temperature. There's a good-sized shop that's attached to the lab that's served by standalone gas-fired heaters, gas domestic hot water, walls constructed with 12-inch CMU, partially grouted with insulated cells. So the wall insulation is really not the best. It's questionable whether that would have even met code at the time. R30 rigid roof insulation and primarily 8x8 block windows with some double pane windows in the small office area in the front. This picture of that lab rooftop unit, strangely, it actually looks like it's in worse shape than the office equipment, which is actually older. And then one of the electric duct heaters inside, and everything inside is just exposed. Now at the lab, they have some unique systems. They do have 3 fume hoods that are tied to exhaust fans, but they're enabled via a wall switch, and the outside air from the rooftop unit, I mentioned its constant volume, is not actually tied to any fume hood operation. And they also have 2 walk-in coolers and 2 walk-in freezers that they use for various research purposes and storage. Their lighting systems, their interior lighting at both facilities is 32-watt T8 fluorescent, and their exterior, they have some 150 to 400 watt HID exterior lighting. So usually the first step when you're doing an audit is to look at the utility data and see what kind of conclusions you can draw just from a high level analysis. Avista Utilities serves electricity and natural gas to both buildings, but there is a common electric meter that's shared between both buildings, which means you can't actually separate the usage between them. They are, however, independently metered on the gas side. Looking at their electric rate schedule, they do have a blocked rate schedule, but in any given month, they don't even come close to using over 250,000 kWh, so they're very firmly within that first tier of use at about 7.3 cents per kWh. On the gas side, it's also a block rate, but they almost always use over 70 therms a month, so they're fairly locked into that second rate at about 87 cents a therm. So I looked at their previous 2 years of usage and plotted the average alongside those. You can see they're fairly consistent from the last 2 years, which suggests they haven't made a lot of operational changes within that time frame. In their total use, it's about 440,000 kWh, 6,800 therms. With their utility costs, there's a strong dominance of electric costs of about 41,000 out of the 47,000 total, which makes sense since they have electric heat, and that's going to be a huge component of that energy use. So one of the main high-level analysis tools you can use is looking at the EUI, or energy use index, or energy use intensity, which looks at the building on an energy use per square foot basis, and this allows you to compare the building in question to another similar building in the same region and get an idea of how that building is performing. So I use the Energy Star for Buildings Target Finder tool to see what an Energy Star certified office building might use, and the target EUI for that type of facility was about 60. Now in this case, it's a little complicated because we have this inclusion of a lab type facility, and a lab facility cannot be Energy Star certified, but it is expected to use more energy than an office building. So just using engineering judgment, I increased that target from 60 up to 70 kBTU per square foot, and I'm saying if we can get these 2 buildings down to the EUI we would expect of a top performing building, we would expect that to be around 70. And if we could cut that EUI by that percent, we would expect to save about $16,630 per year. And you can see the Fish and Wildlife buildings are operating well above what you'd expect a typical office building to be at, not just from an Energy Star perspective, but just from an average office building as well. Here we have an approximated breakdown of the energy use based on end use, and this was developed using the eQuest, the full building eQuest model that was created for the energy savings component of this audit. And you can see the the main energy user here is space heating at almost 64%, which again, this is all electric energy use. But the CVEX 2012 average for space heating is about 25% for in-office buildings. So at this facility, they are operating way above average as far as that component. So the next step is to take a look at energy use and how it compares to weather severity, because energy use is typically highly correlated to how cold it is or how warm it is. On the electric side, since we do have electric heating as well as DX cooling, the electric use regression analysis is going to be require multivariable analysis. It's going to be need to be compared to both heating and cooling degree days, because it is expected to have a dependency on both. And as I mentioned, these buildings are on a common electric meter, so there's no way to split the use and analyze each building independently. So we're just going to have to look at the entire site as one and just do the best we can with that. Looking at the gas use, so the only gas load we have here are the lab domestic hot water, which is an extremely small load, and then the preheat of the supplier at the rooftop units. And so we really would just expect this to have a correlation with heating degree days, and so this would be a single variable regression analysis. But before we can do that regression analysis, we have to figure out what is our balance point going to be in order to calculate the heating and cooling degree days. So started with the raw utility data provided by Avista, and I did calendar normalize it. The meter read dates were around the 20th of each month, which is not quite close enough to the end or the beginning for me to just use it at face value. So I did that calendar normalization to get a better fit when comparing to the monthly weather data. So a regression was performed against balance points from 50 to 70 degrees in 1 degree increments, and I looked to see on both the electric and the gas side, where did the data seem to fit the best. And then once that balance point is selected, then I can generate my cooling and heating degree days from weatherdatadepot.com. And so here's an excerpt from my balance point determination spreadsheet. I trimmed off the side so it's only showing balance points of 58 to 63 instead of 50 to 70, but you can kind of see the patterns of rising cooling degree days in the summer months and rising heating degree days in the winter months. And you can see as the balance point changes, so do the heating and cooling degree days. So running a regression against each of those balance points on the electric side, you can see I have a cooling and heating degree day slope because this is a multivariable regression analysis, and the electric use will be dependent on both. But you can see my R squareds are all really good. They're all above 0.9, but they tend to be the best around the 60 to 65 balance point range. On the gas side, again, I see a very strong correlation between gas use and weather severity, which I would expect. It did seem the balance point was a little bit lower than on the electric side. It was suggesting it to be closer to 55 to 60, and so just as a compromise, I just selected 60 degrees as my common balance point for these buildings. And here we have the average monthly electric use plotted against the average monthly heating and cooling degree days, and you can see a correlation between the weather and the electric use. There isn't much of a gain in the summer months. You can see a little blip here in July and August. Maybe not as much of a rise in electric use as you might normally expect, but it's probably skewed by the use of the lab facility, which is a constant volume reheat system. But you can definitely see a correlation between heating degree days and electric use in the winter months. So running that multivariable analysis against 60-degree balance point, I developed a building signature equation, giving the constant and then the change per heating and cooling degree day. and as I mentioned, the R squared is above 0.9, so I expect this equation to be a fairly good predictor of monthly electric use. On the gas side, here you have gas use plotted against the heating degree days, and you can see a very, very clear correlation between rising heating degree days and rising gas use. And the equation here, again, generated with a fairly high R squared. You might notice that the constant is actually negative, which doesn't really make any sense, but really I just take that to mean that it's next to zero or very near zero. I mean, the only gas load you'd expect when it's warm out is that lab domestic hot water heater, and that load's going to be very, very small. So moving on to operations and maintenance and the current conditions at these buildings. So right now they don't have any scheduling in place or temperature setbacks. Everything is just running full out 24/7. And so the golden question there, why are they doing that, and does it really need to? I mean, there's really no need to run an office building 24/7. And you know, the number one opportunity for energy savings is to turn things off. So figure out how we can achieve that. According to the customer, the reason they're doing this is they just can't recover from night setback conditions, especially in the winter months. And honestly, for them, it's easier to just run it all the time and just forget about it and pay the utility bill. And the equipment operator here is actually the office manager, and she has lots of responsibilities here beyond running this equipment. She really doesn't know how a single duct fan-powered VAV system should even operate on a fundamental level. And this was something she kind of inherited, and then she's just accepted it as that's just the way it is. This equipment is approximately 12 years old, and normally I wouldn't recommend full mechanical replacement after 12 years, but the 24/7 operation for who knows how many years has probably accelerated that replacement schedule. And last thing to note, commissioning was never performed on these buildings. And at the time, it was not an energy code requirement as it is now, so it's not terribly surprising. So let's take a look at some observations I made on site. One of the rooftop units at the office building, the disconnect handle was broken and just sitting on the roof about 15 feet away, which isn't an energy concern, but it's a definite safety hazard. And so the customer was made aware of that immediately, and they did make a commitment to get it fixed. The electric hot water heaters are installed up in the ceiling, and it's a little hard to see in that photo, but I drew a little outline. That is as close as I could get to that hot water heater. So again, it's not really an energy issue, but certainly a service concern. If that thing were to fail and need to get replaced, that would be extremely difficult. I did notice some missing duct insulation in one area of the building on probably a 7 or 8 foot run of large spiral round duct. It was insulated on each end of that, but for some reason part of it did not get insulated, and I don't know if that's an isolated issue or if there's something a little more systemic there building wide, but this was the only area I noticed it. And in the lab building, in the shop mezzanine is where most of that rooftop unit ductwork is routed. And that rooftop unit doesn't even serve that shop space, but all of that duct is uninsulated, which means in the summer months that's going to leach a lot of heat from that shop area and reduce the effectiveness of the cooling on that unit. The lab had a apparent failed domestic hot water circ pump. The owner didn't even realize they had a circ pump, but it was not operating, and they had a little wall switch that didn't appear to do anything. The shop shop unit heaters are wired to a couple outside air dampers that are supposed to open for combustion air to enter the space when those units are enabled. But those dampers are just stuck open, which means in the winter months there's going to be hemorrhaging heat just constantly. Then on the office units, the condensate piping was not the best. They attempted to put a P-trap here, but it really doesn't look like it has the sufficient depth to be effective. It also doesn't have a means to clean it in the event that there's a blockage. On the lab unit, they didn't even put a trap in at all, so it's just open to the exterior. And here's an example of a properly built trap that has that, the sufficient depth for it to be effective, as well as a cap or some kind of plug on the top so you can clean it if needed. So these aren't all energy concerns, but certainly operational concerns that should be looked at. So looking at the building automation system, this was kind of the crux of a lot of this audit in trying to figure out how do we get these systems to not run 24/7. So first I looked through the logic and tried to identify any energy savings strategies that I would expect in a building like this. So HVAC scheduling, the system is definitely capable of doing that, but it's not actually utilizing it. Same thing with temperature setbacks, capable but not being used. There is a supplier static reset algorithm programmed in, but due to the set points that they have plugged into the algorithm, it's not actually doing anything. You're probably noticing a trend here. Morning warm up and cool down, because they're running everything 24/7, they're not actually using it, even though it is programmed in there. The office supply fans are variable speed. They're modulating the 1.5-inch water column set point, and the supply air is being reset between 55 and 75 degree limits. But due to the limited staging on the heating and cooling, it's extremely difficult for them to actually achieve the set point that they want, especially in heating mode when the fan goes to a low speed condition and now you turn on one stage of heat and you get the 20-25 degree temperature rise and they overshoot their set point and then it turns off and now you're under. So there's a lot of cycling of equipment. This is a summary of their current schedules and set points. Everything's operating 24/7. The lab shop cycles 24/7. The set points are weighted averages based on peak cooling airflow provided to each space, and they're largely appropriate. 70, around 70 in heating, around 75 in cooling. The lab heating set point, that's a little low, but that's only going to save energy in the end, but it could lead to some comfort complaints. And the lab shop set point is a bit high. Considering a shop is typically less insulated than a typical commercial building, and they have these large roll-up doors, maintaining it at 67 degrees all the time, especially overnight when it can get extremely cold, it can waste a bunch of energy. So here's a screen grab of one of the office air handling units, and I hope it's come through your screen okay. Just to identify some of the anomalies I found. So the supply air, after it leaves the coils, there's a T in the ductwork where it splits and goes to different areas of the building. Now, these two temperature sensors should be reading about the same thing, but they're reading almost 12 degrees apart. So it could be bad sensor location or it's out of calibration, but something is definitely not right there. The outside air damper here is commanded shut, but if you look at the return air and the mixed air conditions, we have a return air of 72 and a mixed air of 58. So that suggests that the outside air is actually open quite a bit. And if you change that setting, if you override it, you don't see any change in the mixed air temperature sensor, which suggests the outside air dampers probably failed in some fashion. The filter differential pressure sensor is reading 0, could be a failed sensor. Even a clean filter should be reading something. And the same with the building pressure, it's reading 0. On the other air handler, we see some similar issues with the filter DP sensor and the building pressure sensor, both reading 0. In this case, the unit's actually trying to economize, and so it's trying to force the outside air damper fully open, but between the return air and the mixed air, we're only seeing about an 8-degree drop. And again, when you go in here and you override the command, you don't actually see any change in the mixed air temperature. So the outside air damper's probably failed on this unit as well. And the VFD speed here was showing 100%, and this was a 35-degree day. So we really wouldn't expect it to be peaked out like that, but now it may have something to do with the fact that in this case it was trying to economize. When I looked later, it did appear to be modulating like it was supposed to, so it could just be I grabbed it at the wrong time, but operating the fan at 100% is just going to lead to excessive fan speed and potentially additional reheat energy. The static pressure reset, I had mentioned that the algorithm was in place, which is this block diagram here. So it's there, and it's trying to do what it was programmed to do, but the minimum maximum set points are set to 1.5 inches, so it's not actually able to do anything with it. So as I mentioned, everything's operating 24/7 because they said they can't recover from night setback. Well, the customer here is not very technical, and they can't tell us why. They just know it doesn't work. So as a test, we over a weekend we allowed the spaces to fall back to 55 degrees, just to watch the following morning, just to see what happened, and hopefully find, what's the smoking gun here that the customer doesn't know what the problem is. And if we can figure out what that is, then we can re-implement the HVAC scheduling and temperature setbacks. That's our top opportunity for energy savings. So the results of that test, at the office, most of the spaces actually recovered pretty well. 9 spaces struggled a little bit, and 5 spaces struggled significantly. Taking a closer look at those 5 spaces, 4 of them appeared to have failed electric heat at the VAV boxes. So I went through and tested every other box in the building and found 2 additional boxes with failed heat. So with those 6, that accounts for about 22% of the total reheat capacity at that building. Now, I did not figure out what the problem was, but I did talk to a service technician who has experience with this, and they mentioned that with these electric reheat boxes, they have a number of safety devices, and he said he's almost certain that one of those safety devices had failed. It wasn't necessarily a bad coil, which would likely mean it'd probably be fairly inexpensive to fix. So the results at the lab, all of the spaces struggled a little bit, and I'm guessing that's due to the poor wall insulation, and one of the zones has a pretty good size roll-up door, so that's kind of expected. Poorly insulated buildings just simply have a much harder time recovering. So there's likely still some opportunity there, but maybe instead of going back to 55 degrees, we go to 60 or 62. That's still better than running things all the time. And here's a trend graph of all 34 VAVs and kind of how they recovered that morning with the occupied start time of 8 o'clock. And you can kind of see the trend of the good and the bad. It's kind of a spread, but most of the spaces were up to, right around 69 to 70. Some were even up to over 72 at that time, but there were some that did struggle to get there in time. And this wasn't an excessively cold night. It was probably around 20, 25 degrees that night, so the problem would have probably been more apparent, if it was a 0-degree night. And this is a screenshot of one of those VAVs. So you can see here the electric heat is on, but we're only seeing about a 2-degree temperature rise across the coil. And that temperature rise is likely due to sensor calibration. I'm assuming the heating coil is not actually doing anything here. And as I mentioned, that's typical of 6 VAVs. So in summary, when looking at the BAS, I think it would be really important that all these systems be properly commissioned. They have these failed outside air dampers, failed electric heat. It was never commissioned in the first place, so there may be even other issues that would be made apparent during more detailed functional performance testing or point-to-point verification. Some alarm logic should be implemented to indicate failed electric heat. The customer had no idea that these reheats had failed. They do have alarms in place for low space temperature, but because this is kind of an open office, if one heater fails, the other heaters can kind of pick up the slack a little bit, and so it's hard to identify when a specific heater has failed. And then the energy saving control strategies that are already programmed in place should be re-implemented, and maybe include some functional performance testing as part of that retro commissioning effort. Specifically on that static pressure reset, who knows why it was disabled in the first place? There may be a reason for that, so we have to be cognizant of that fact. So moving on to the facility improvement measures. So the low cost or no cost measures, these aren't necessarily quantified. These should be done at an absolute minimum. So they should re-implement some equipment scheduling as well as temperature setbacks, and they don't have to get super aggressive with it, but something is better than nothing. They can look at re-implementing that duct static reset. They can turn that lab unit into a kind of a crude VAV system. They already have the VFD on the unit, and they're not really using it as a lab very often. At the office, they should be repairing those outside air dampers. They do appear to be leaking quite a bit or stuck in place. So if they can fix them, that can save some energy, that can re-enable economizer operation, and potentially improve the indoor quality as well. At the office, there's some supplied air ductwork that can be insulated, and they should probably do a deeper dive into other areas of the building to see if there are any other sections like that. As well as the lab, they can insulate all that supply air ductwork above the shop. They should be fixing those unit heater combustion air dampers. And that lab shop, they really should install a programmable thermostat. Because right now it's a single set point thermostat, doesn't even have capability of programming, and they're just maintaining 67 degrees all the time. On the capital cost improvement measures side, retro commissioning is top of the list. I feel like if they can identify and repair these issues we're finding, they can re-implement the scheduling and setbacks and other controls optimizations, and that's going to be the biggest bang for their buck. They did mention that they want to replace the rooftop units, and we agree that that's a good recommendation. They will get improved heating and cooling efficiency, as well as having better control of their supply air temperature set point through installing a unit with modulating heating and cooling control. They can reduce their electric reheat energy. At the lab building, they also want to look at replacing that equipment. They've had numerous issues with it, and we agree with that. And while we're replacing that equipment, we would recommend they go to a single duct VAV type system, because they're not really using it much as a lab, and even if they do turn those fume hoods on, there's no reason this converted system wouldn't be able to return to that original design condition. At the lab, we'd recommend an exterior insulation upgrade for reduced heating and cooling energy. They also have some aesthetic concerns, or they're really not a fan of how that big block building looks. On the lab freezers, we're recommending that they install it's an aftermarket product called a key-to-therm module that will take control of the reheat cycle on these units, the defrost cycle. So normally these defrost cycles are on a timer, which means they're going to defrost more than necessary, whereas this will actually do it based on an as-needed basis, and it's a fairly inexpensive add-on, and it tends to have a pretty quick payback. On the exterior lighting, they could go to a LED lighting, basis of saving, improved efficacy of the fixtures, and they could also look at installing a separate electrical meter at the lab. And the savings there wouldn't be directly quantifiable, but knowing how much energy you use allows you to notice irregularities and can lead to indirect savings. So the energy savings calculations, the primary methodology here was an eQuest simulation, and that was for the Office RCX, the major mechanical measures, and the lab exterior insulation upgrade. The lab freezer defrost optimization, that was done with a vendor-provided spreadsheet with a 75% D rate. The LED lighting upgrade was done by others, but I did do some incentive analysis on that, which is why I'm including that measure here. And the separate electrical meter, those savings there aren't quantifiable necessarily, so I didn't do any savings with that. So in the eQuest model, here's a Google Earth shot of the two buildings, and here is my my eQuest model that you can see emulates the buildings pretty well. And the most important step here is the baseline model calibration. That is absolutely critical, and often takes about 80 to 90% of the work whenever you're modeling an existing building is just getting that model calibrated to the bills. So average monthly electric and gas use was calculated from the previous 2 years, calendar normalized. The model is created using drawings, what we know from looking at the BAS and engineering judgment. And regarding any unknowns, it's most important to have accurate inputs for things that we're proposing to change. So if we're messing with the HVAC system, we really want to dial that in, but maybe getting the windows exactly right isn't quite as important. So it's kind of half art, half science, never perfect, and sanity checks and peer review are really critical when doing these models. So with weather normalization, eQuest model, they typically use the typical meteorological year TMY file, which the file here using a 60-degree balance point, you can see from the actual weather there's actually a pretty significant difference here. And if you have a building with significant dependency on weather, that can make a big difference. So the eQuest model simulated using the TMY data, regressed with the chosen balance point, and then normalized to the actual heating and cooling degree days. And this is our build use. My original, my raw use, which you can see is a little high, but then once I normalize it, I can get down to within very close % of actual use. So the lesson here, accounting for weather, is extremely important. And if you don't do that, you can kind of spin your wheels trying to fit the model to data that's not really fair to compare it to if the weather file is vastly different from what the build data had seen. So you can see electric use, I got that tuned fairly well month to month. Same on the gas use. The dashed line is the kind of the raw output, and then the red line is after normalization. So you can see it makes a big difference accounting for that weather. And then once the baseline is tuned, we create new models, and then we simulate those as new models. And every model will do its own regression analysis because every model is going to be unique and have a different signature equation. And so each one's going to be normalized. And the intent is to bring everything back to that actual baseline usage and actual baseline weather. And the energy savings are calculated as that baseline use minus the proposed use. And to prevent the overstating of savings, I had to cascade certain measures together. So in the case of the office, I would assume the RCX is done first, and then the office RTU upgrade comes second. At the lab, the VAV conversion first, and then the insulation upgrade second. Here's just kind of a summary of all the different models that I put together and the monthly usage. So that's the electric side, and then the gas side. Here's a screen grab of that key to therm vendor provided spreadsheet. So these are the inputs I put in, and those were field verified, and it spits out a kWh savings at the end. So moving on to the financial piece, so incentives. The Vista utility offers two types of incentives. We have prescriptive, which are fairly simple. You install a thing and you get some money back. And there's really nothing to prove out. You just need to prove you bought it and installed it. Now, custom incentive is a little different. They typically pay 20 cents a kWh and $3 a therm. And it can apply to anything, or I should say most things, that don't fit the prescriptive program, but must have less than a 15-year simple payback. Vista will perform their own analysis, and they won't accept anything that I would put together. And for custom incentives, they will typically require a little bit more rigorous verification. So each measure, RCX measures can apply. The major mechanical measures would be greater than a 15-year payback. Exterior installations at 40 cents a square foot. The defrost optimization, if we can meet a 15-year payback, that'd be 20 cents kWh. Exterior lighting is based on fixture type and wattage. And the meter would have no savings, at least no quantifiable savings. And here's just kind of an overall financial summary. The big standout here is the retro commissioning, which has a very impressive rate of return of 32.2%. The major mechanical measures have a poor rate of return, but it's something they want to do anyway. And major mechanical retrofits typically do not pay for themselves very well. So that's not surprising. Same with the exterior installation upgrade. The defrost optimization and the LED lighting have decent paybacks, or excuse me, returns. And the electrical meter, who knows what that would be. Measurement and verification. Start with a little explanation of the design build ESCO model. So this is all specific to Washington State, and it's going to vary by state, but in Washington, public entities typically use a design bid build process to procure any major work. Customer will manage that bid process, and it takes a lot of time and energy and money, and they're often obligated to go with the lowest bid and least expensive equipment. But Washington does allow design build process to procure work for, quote, cost-effective project, which is an admittedly vague term. These projects should pay for themselves within the life of the equipment. Is that really enforced? It's questionable at times. The main benefits we see, at least with McKinstry's clients, is it allows for quick turnaround, more control over subs, and the ESCO will manage that process from beginning to end. So the original intent of this audit was to develop a design project, and the key component there is guaranteed costs and savings. So if the energy savings are guaranteed, they must have measurement and verification, or M&V, which is a professional service and it costs money. So how do you do this without eroding your savings? And it doesn't make sense to tell someone, you're going to pay me $12,000 a year to verify $9,000 in savings. So an M&V plan was developed based on McKinstry standards and IPMVP option A, and I won't go over all the options for the sake of time, but option A partial measurement with stipulations, so certain key parameters are verified, such as schedules and set points, and we make sure do these measured parameters line up what we expected or what we were counting on for savings. And other parameters can be stipulated, which are just agreed with the client and not verified. The common one being lighting burn hours. You might just say to the client, can we agree that as the basis for savings, we're going to assume 3,000 burn hours a year? And they say, yep, okay, and that's that. The other option utilized here is calibrated simulation. So I take the verified parameters that were measured through option A, put those into the energy model that was created previously, and run the simulation again with these verified parameters to calculate the verified savings. And here is a sample M&V plan, or at least an excerpt from one measure. These M&V plans are a bit rare to get through, but just going over the headers, we have key performance indicators. What are the things we're expecting to change? What's the baseline or existing value, or the proposed value? What are we stipulating? Audit stage task is, how did we verify the baseline? Post retrofit, how did we verify after it's installed that it meets our proposed? And then annual tasks would be, what do we do at year 1, 2, or 3, or however long we pay for it? So some misconceptions is M&V is often hard to explain. People think we're looking at bills. Why don't my verified savings match what's on my bills? And verified doesn't necessarily translate to actual because of all these stipulated savings and and weather changes and that sort of thing. So this M&V method allows savings to be expressed in an apples-to-apples comparison. So that option C of utility meter analysis is typically not done because lots of things go into that metered use that may not be part of the project that we actually did. So some additional measures that were considered but not performed. Looked at a hot water system conversion for the electric reheat system. The savings here wouldn't justify the cost. These aren't very large buildings, and so the economies of scale just don't work in our favor. Interior LED lighting upgrade wouldn't work very well because electric heat is the primary heating source here, so savings in the heating months are essentially negated, and existing T8 lighting is already relatively efficient. The defrost optimization module could be installed on the coolers, but because they maintain a higher set point, the return wouldn't be as attractive. So the final results, good news. Customer intends to move forward with all the recommended capital measures except the new electrical meter and the lab installation upgrade, which they just did not see as a high priority at this time. They're a happy customer. This is kind of an experiment for them, and they're going to recommend our services to their other offices in the state. But the bad news, Washington State capital funding has not been approved, so there are a number of public projects that are being held up as a result of that, and they're going to reconvene within the next few months to hopefully resolve that, and then we can pull the trigger on this. So that's all I got. Thank you for your time. I had a picture of the nice bottle of scotch I have waiting for me at the conclusion of this project and program. Are there any questions?
Well, I have one right away. You said that the funding wasn't there if this was put together as a energy savings performance contract, a lot of effort was put into the audit, a lot of time. So
Correct.
Does McKinstry recover that?
Yes, we do typically charge for an audit.
Okay.
Whether we make money on the audit is questionable, because sometimes it's, if you present a customer with a $40,000 audit fee, that might scare them away, right at the start. And so it's we do recover at least most of the costs. If we can be real efficient, we can make a little bit of money on the audit. But our ultimate goal is to deliver a project in the end. And if we don't think we have a decent chance of that, we probably won't take the audit on.
Okay. Yeah, clear at the beginning, there was a really interesting application mentioned, and I wanted to make sure that Chris and Jason heard this, that the lab was designed as a lab, wasn't always used as a lab, but it was all the time running, but it was all the time ventilated like it was a lab. And I'm not sure if you explained, and I just missed it, the hope, you explained it to me at one point, Derek, of how that might be controlled in a more sane way, because sometimes it is used as a lab, and when it is, it has to perform that way for safety, and then how you might do it. So can you just fill in the design piece there, because I think it was very interesting.
Yeah, I didn't cover it very well in the presentation. You're right. So basically the design intent, well, I guess let me back up. Are you referring to modifying the existing system,
Yes.
or going to single duct VAV?
What I remember was that it was going to be 100% outside air whenever it was being used as a lab, but then not when it wasn't. That's the piece that stuck in my mind. I wanted to come out.
Well, we did look at the potential for essentially adding in a return air system to the unit so that it wouldn't have to be 100% outside air. And I discussed that with our engineering design manager, and he wasn't sold on the idea. I mean, basically the intent would be, if the fume hoods aren't running, just recirculate air, provide minimum ventilation, and then if the fume hood turns on, close the outside air completely, and then go back to 100% outside air operation. The issue we saw was, even if you close if you close the return air damper, you're still going to get some leakage.
Yes.
And so you're not going to be able to fully return it to its original condition. So in the end, we didn't propose a return air system. We would keep it as 100% outside air, but if we could at least reduce that outside airflow in any time when the fume hoods are not operating, that would be a substantial improvement, just because this is 100% outside air, and that's an incredibly energy-intensive unit.
So then, when a fume hood is active, does the system revert to constant volume?
Right. So the supply fan would ramp back up to 100% speed,
Mm-hmm.
and it would basically operate exactly as it's operating right now.
Mm-hmm.
Now, looking at the trend data, those fume hoods haven't been running for at least 3 or 4 months, which tells you how often they actually use that building as a lab. But they still want it to remain a lab. Right.
So whenever it needs to work as a lab, safety trumps everything, and you go back to the conservative approach, and that's fine. But if no fume hoods are on, then you can modulate the amount of air and reduce the scale of the problem.
Exactly.
So that's a great example of the battle in design. It's a crossover in design to energy, and it's not a battle, but it's a comparison. You have to be aware of the needs of the building and make adjustments where they don't step on the functions of the building or anything in safety.
Can I ask a follow-up question on that?
Go ahead.
Sure.
The new VAV system, what is the ratios, say, of the lab airflows to the kind of standard airflows that have been running for the last 4 months? Did the new system does it have to be oversized?
Well, it would still have to be sized to provide the supply air required for lab conditions. Now, if it doesn't need that, it would be able to ramp back, from the VAV box, but everything would still have to be sized according to the 100% lab requirements.
Is there a big difference there?
As far as sizing of the heating and cooling components?
Yeah, but basically in CFM.
I don't think in CFM there would be a huge difference, but certainly in the heating and cooling capacities, because if you have a 100% outside air unit, you need a heater that can heat up 0 degree air up to 90.
I see.
Whereas if you have a more standard system with return air, instead of having to heat 0 degree air, you're only heating 55, and so your delta T is cut in half or even more. So your gas heat might be a third of the size or half the size.
Right. Okay.
So I had a comment when I saw the end-use pie diagram that you developed. I wanted to compare it. Yeah, if you can flip back to that. That one right there. So when I look at the CBEX pie diagrams, their categories are different in one important way, and that is that they have a separate category called ventilation, and I called and clarified about this at one point, and the heating that goes on for heating up cold air coming in the winter goes into the ventilation category for CBEX, and here I'm guessing that I guess the chart you're showing says CBEX. The one I'm used to seeing a ventilation category. Am I not seeing it? Or did you combine it?
I may have combined it.
Okay.
I'd have to look back at the docs. It may very well have been included somewhere.
What I thought I was looking at, and I didn't notice the CBEX note on there, I thought this was the end use that eQuest had produced as one of its standard charts, and I just was going to comment that they may not have been exactly overlayable.
I had to. I took the eQuest outputs and created this chart on my own.
These are eQuest values or these CBEX values?
These are eQuest values for this building.
Okay. So yes. So there's an extra category in CBEX where it says space heat. That will be the thermal loss of the building. It will not include the ventilation heat. That was what I wanted to add.
I see. Okay.
So just a comment.
Okay.
And let's see. I was curious. You showed the incentives, which was good to see. Did you find cases where the economic parameter, whether it was simple payback or rate of return, went from bad to good or not acceptable to acceptable because of the incentives? Because that would be something that the utilities would like to hear, because that's what they hope their function is to take a project that wouldn't have made it and cause the thing to go forward. They like to hear that, if that's true. Did you find that to be the case?
I would, let's see, just looking at this table. I mean, on this exterior insulation, the cost here is so far above, anything the incentive would offset.
Right.
That wouldn't matter. The lab defrost, I think that would make sense either way. I don't have the simple payback here, but simple payback would be about 6 years or so.
Okay.
But then with that incentive, that cuts that down drastically.
Yeah.
The LED lighting, that also makes a fairly big difference. I do know that this cost here is a little inflated from where it might normally be expected, because they have these decorative lights that are apparently very expensive to replace.
Yes. Okay.
And so that incentive there that can take a pretty big chunk out of that $18,500. So I think the LED lighting upgrade would still be acceptable, even more so with that incentive.
Okay, thank
If
you.
we replace those decorative lights with something a little more basic, then it would look even better.
I got a couple of O&M questions, but first I want to be sure I hit this one. You showed at the beginning the energy use intensity was notably higher than you expected it, and like you knew something even from 30,000 feet. It was something's wrong here, and you did find a number of things wrong. So after the savings were calculated, did you have a chance to say kind of a what if they did the things you recommended or the things they agreed to do? How far down? Would it have come down to the average, or would it have come down to an Energy Star level? Where would it end up?
I did look at that. I didn't include it in here. I believe the final energy use index would have been around 55.
Well, very good.
Which is actually a little lower than I anticipated. But thinking about it more, especially considering they have electric heat, which is going to give them some EY gains, compared to gas heat. Even though it costs more to use it, on paper it makes their EY lower. And also considering the pretty drastic changes to that lab building we'd be looking at.
Yeah.
Where it wouldn't really be a lab building anymore. So I guess at first blush, I thought, well, that's a little low, but after thinking about it some more, it made a little more sense.
It does seem low. Let's see, I'm hogging the microphone, but having worked in a humid climate and troubleshooting and designing, and whenever I'd see a P-trap that either was not a P-trap or was a not good enough P-trap, what that means is the P-trap's there to keep the draw-through fan from pulling air in.
Right.
It allows it to drain. So the first thing I would have done if I saw a poor P-trap is open up the door to see if it was ponding full of water in there. I was wondering if you saw anything like that, or if there's enough moisture in your corner of the world that you even see that.
I didn't notice any ponding. It's actually pretty dry here.
Okay. Yeah, I found one just the other day. Even in Colorado Springs, the trap was just gone. And opened it up, and there was like 3 inches of water standing. The bottom of the coil was underwater. That's the risk for a draw-through. If it's a blow-through, air comes out, it drains just fine. Plus, you're air conditioning the outside world. That was just a curiosity. Well, I guess the last one, since it's a government facility, right?
Correct.
So, speaking from experience for the small piece of government that I worked for, I was curious if there was any mechanism in the management that provided feedback, meaningful feedback to encourage people, not just encourage, but make them put it on their radar screen. Do they care about energy savings, or is this just whatever it is, it gets paid for, and somebody else? Are they accountable? Did you see any of that, or are you aware of that?
Well, it's kind of interesting because in my interactions with the office manager who operates this equipment, she seems genuinely interested in energy savings, but I don't know why they haven't taken measures until now to do something about it. But I don't have a good feel for what her boss, thinks. Maybe that direction came from above, but I did mention that they are kind of using this building as a test case for design build ESCO. And if it works out here, they want to pursue that elsewhere in the state. And so I guess it's conceivable that effort came from somebody high up.
For example, if there's a high utility bill, does it come out of their operating budget? Is there a consequence or not? Maybe it comes down to that.
I'm not sure.
Okay. I was just curious because what I've seen in the government that I work for, when it gets big enough, it's just the utility bill comes in, it just gets paid for, and then the facilities folks don't even necessarily see the bills. It just happens, and so it's really easy to not care when it's somebody else's money, right? That's what it comes down to. Well, I'm glad that they were interested, whether they were forced to because their operating budget was shrinking, or if they just wanted to. It's happening either way. That's good.
Yeah, and I think the number one thing that she appreciated was just the education.
Yeah.
As I mentioned, she doesn't know what a fan-powered VAV system even means, or how it's supposed to run. So yeah, they seem pretty happy with what we've provided them.
Well, those were my questions. I've been hogging the mic. Chris or Jason, any more questions?
Did you confirm the outside air dampers were broken?
Well, the two things I did was one, while I was in the building automation system, I forced them open and closed and tried to look for any response in the mixed air temperature.
Mm-hmm.
And I didn't see a response in either way. Either open or closed, there was no change whatsoever. And so I went on the roof, and I had the office manager manually open and close them, and I couldn't get to the dampers without dismantling part of the unit, and I wasn't going to do that. So I did what I could to try to listen for any actuators moving or dampers moving, and I couldn't hear anything at all changing while I was up there.
Thank you. On about slide 63 or 64 about the order of recommendation, it went by a little quick.
Yeah, I knew I was running out of time, so I started to speed up a little bit.
So I'm curious here on this one why maybe I'm reading it wrong. The insulation comes after the VAV conversion? Is that the recommendation, or just how you're simulating it?
Well, you can do it either way,
Mm-hmm.
but the way I typically do it is, which measure is more likely to happen.
Mm-hmm.
So in this case, at the office, we know that RCX is probably going to happen. I mean, we had already talked to them about it, and it's a relatively low cost, high savings item. So that makes sense. And then on the VAV conversion, that's kind of the big saver there.
Mm-hmm.
And we also knew that was a higher priority for them than the wall insulation.
That makes sense. So curiously, do you know how much difference in the VAV conversion sizing the wall insulation would affect? How much it would reduce that load?
I don't, but you could conceivably drop a kW or two at each VAV.
Right.
And that is something that could be done if they choose to move forward on that option, and we do a full final design of the new system, then that is something we could consider.
So you can replace this equipment up there in Washington, which I know has a strict energy code, and they won't make you go back and fix this insulation deficiency first?
No, basically the exception in the code is that they will not force you to bring up to code something that met code at the time of installation. Now, as I mentioned, it's questionable whether or not that wall actually meets whatever the code was back then.
Right.
But presumably some official,
Has a stamp.
somebody signed off on it. Somebody
right.
from the building department or code reviewer They will not force us to bring that up to code necessarily if we're replacing the mechanical equipment.
Adding new equipment's where you get into trouble with that, right?
Yeah, I mean, it's alterations and dealing with existing buildings is always kind of a gray area. We deal with it all the time, and thankfully the code officials have been fairly lenient about not forcing us to bring a whole building up to code just because we want to replace a chiller or something. And then they seem to understand the impracticalities and the fact that having to bring these other items up to code would just mean they can't do the project at all because it would cost too much money.
Thank you for that. That's all my questions.
Have anything, Chris?
Yeah, I'm always going back to controls. I'm just curious, what kind of building automated system they have? Was it a canned programming? Could you write equations in it?
It's automated logic, which let's see, so their logic is based on block diagrams. I'm trying to find the screenshot I had. A little hard to see, but basically you just kind of create these plug and play diagrams where okay, I'm going to take some set point here and I'm going to multiply it by some value and then throw it into something else. And the nice thing about these block logic diagrams is, as somebody without a lot of programming experience, I can usually work my way through this and kind of figure out what's going on. It's not like I'm reading C++ or something really obtuse.
No, I'm familiar with that. You're right.
So, but yeah, this is essentially how their logic looks.
Did you work through any of it to see if it had any? I mean, if it seemed to work or whether it seemed to overlap or anything?
I didn't do too deep of a dive. I mainly looked at things like these set points here. I'm not as familiar with working through these logic diagrams. I'd probably have to bring in one of our commissioning agents who deals with these, day in, day out, and know exactly how to read them like a book.
Mm-hmm.
Anything else?
No, that was just curious on that.
Did the BAS system already have all the points enabled to track all those room temperature set points? It seems like it was pretty actively used, like 3 screens down, 48 there. Or did you have to put that in, or was it already enabled?
The points were enabled. I had to make sure they were trending properly.
Mm-hmm.
But yeah, they were all there. We just had to download the data.
Get it and organize it. Very
Mm-hmm.
good.
Do you have
Okay.
another question? Do you do a lot of these projects like this, Derek?
Yeah, we've done a large number of audits like this. Normally, I'm not the one doing such a deep dive into these building specifics. Like I said, our commissioning guys know building automation systems in and out, and so we would probably task them with discovering some of these things. And I kind of lucked out on this project that they had automated logic, because that is the one system that I have some familiarity with and know how to get trends and override settings and do everything I need to do. But this project is kind of our bread and butter. We do a lot of municipal buildings such as these, a lot of a lot of schools. I mean, 95% of our projects are public. And they want to use that design build ESCO model just to have control over the project and the subs we can bring to the table, and then the speed at which we can do the project. I mean, we've turned around major school retrofits in 4 or 5 months.
Steve, your comment about whether people care how they spend their money really hits home in the school district. I get really frustrated from whether we're irrigating water to the turf, or whether we're, it's school districts just they care, but they don't care. They want green grass, excessively green grass. It's always a struggle.
Sure. There's a balance there because use your school as an example. The school has a mission, which is educating and nurturing students in the community. That's the focus. So the rest of this facility stuff and utility stuff needs to be provided, yes, but the balance is to be stewards of that, whatever that costs, and not be oblivious and wasteful of it. There's a balance. Good. I'm going to turn off the recording button, if that's all right.
Yeah, sure.